Hello, everyone. Welcome to this week's Crunch seminar. Today we have one speaker, Dr. Honghu Liu. He's an associate professor in the Department of Mathematics at Virginia Tech. Dr. Liu's research focuses on using dynamical and statistical tools to design effective low-dimensional reduced models for nonlinear deterministic and stochastic partial differential equations, as well as time-delayed systems. Some main application areas of the developed techniques include bifurcation analysis, phase transition, optimal control, and stochastic closures for multi-scale systems arising from nonlinear sciences. Dr. Leo, thank you so much for your time today. And with this short introduction, you can start.
Thank you so much, Juan, for the nice introduction and also for the invitation. It's very nice to come here and give this talk. So I will be talking about recent work that we published on nonlinear dynamics about using some information theoretical tools to derive sparse reduced order models. This is a work, joint work with Nan Chen, who is associate professor in the math department at the University of Wisconsin, and the work is supported by National Science Foundation. The goal here is so we try to find a framework where we can identify a hierarchy of reduced order models where we can adjust the degree of sparsity in the identified model without relearning each time the parameter estimation procedure, right? So we hope to find a mechanism where the building block terms can sort of being ranked, right, through a strategy. So when now if the building block terms, the importance of them are ranked, then I just need to select my cutoff threshold, right? Then each time I do that, I get different reduced order models with a different sparsity structure. So that's the idea. Of course, nowadays, data are everywhere, right? We sort of have a problem of having maybe too much of the data to handle, but then why do we still care about enforce some sparsity in the learned model? One motivation is coming from, for instance, say, of course, for many disciplinaries, we have a lot of data, but actually for some other disciplinaries, maybe the data either because it's too costly to collect the data, right? For instance, some biology experiments, and also it's just sometimes we don't have access to abundant data. For instance, in climate dynamics, when we measure the El Nino phenomena, right? So the observation, we only have the past few decades where we have the equipment to observe, for instance, the sea surface temperatures. Then when you average it to monthly data, then it's really just a couple of hundred data points, monthly data points. So not really too much data. That's why to look for sparsity in the learned reducible model, there is still a virtue of doing that. And of course, in the literature, there are already many established methods and well-researched methods. For instance, there's a cost function-based approaches. For instance, the compressed sensing, LASSO, and more recently, there's the very popular method called SINDI. It's a sparse identification of nonlinear dynamics. But our approach is a little bit different. Instead of our cost function-based approach, for instance, LASSO, on top of the regular least square, it just add another term where there's a L1 minimization term, where the L1 minimization actually enforces sparsity, where it forces many of the coefficients to be zero. Right? That's we get sparsity because of the cost function that we use. And instead, we're looking for another angle from some tools from information theoretic background. And that approach, there is already also quite a few decades of research on that. For instance, it can be traced back to Arkik, his early work in the 1970s. Of course, initially, the idea was to quantify information flow or some potential causal influences of one set of data onto another set of data. Right? But when we think about the reduced order models, when we have different terms, right, we want to construct a dynamic equation for certain quantity, right? So then it's going to be a set of either ODEs or stochastic differential equations. Then in the stochastic equation on the right-hand side, we have different building block terms, right? So then we can treat this as one set of the data. Then the other set of data would be like the time derivative of the quantity where we aim to model. Right, so then there's the information flow there, and that's where kind of the tool comes into play. And the key concept, underlying concept, is called entropy, and there are many different variants of it. And in the next slide, I will start to review a little bit. So I don't know the audience here, but I'll just try to recall some basic definitions from the information theory. But of course, compared to these two approaches, cost function based approach and the information theoretic approaches, there has been some recent work trying to distinguish what are the advantages and the disadvantages of the two approaches, right? So, but for instance, there's a recent paper by Monani and Swen and Bolt. It was published in Chaos, where they identified some potential barriers, for instance, the severe collinearity, or when there's a noise or some rare outliers in the data, then the information theoretic approach can provide more robust results compared to purely cost function based minimization techniques, right? But of course, there's still developing. It's still developing. It's not definite like which method is really the best, or maybe could be like for some set of data, one approach could perform better than the other. There's no definite answer yet, right? So that's kind of where we stand. Then moving into the structure of the talk, so I will first review some basic concepts, as I said, right, from information theory. Then I will introduce the causation-based framework. And after that, I will show the results on our PDE model called Kuramoto-Sivashinsky equation, and summarize and some outlook will be provided at the end. Okay, for information theory, of course, myself, I'm not an expert on this topic, but here's a textbook I find very useful, and it's very informative and covers extensively various topics by Cover and Thomas. The theory about information, of course, it was built upon the foundational work, the pioneer work by Claude Shannon back in 1948, right? So he wrote this landmark paper titled A Mathematical Theory of Communication, which laid the foundation of the modern information theory. And what's important about Shannon's work, the most foundation one is about he made the information a well-defined measurable quantity, like using his own words, like he was saying, the information can be treated very much like a physical quantity, such as mass or energy. And our underlying concept is entropy. And the one Shannon proposed was it's called Shannon entropy. It was dealt with for discrete random variable, where given a random variable x, right? So you say we know the probability mass function of this random variable, then the Shannon entropy is just defined by the formula here. What you do is take each possible state of the random variable, right? So you take the log of the probability probability mass function, evaluate that value, then multiply the probability itself, then sum up among all the possible states, and then take the negative of it. And here's the log. Usually there are different bases we can use, right? But the basis from a mathematical point of view, it's not important, right? Because you can change one base from another by multiply a conversion factor. But base 2 is a popular choice, and we'll see in a moment why that is the case. Of course, then we can extend to the continuous random variable, where you replace the probability mass function by the probability density function, and the summation becomes the integration over the possible states of the random variable. Right, it's called differential entropy. Then when we look at it, right, so this formula, if you don't have previous exposure to information theory, right, then it does not really talk much, right? Then maybe let's look at the just an example. In the case of Shannon entropy, we're dealing with discrete random variables, right? So intuitively, the Shannon entropy actually provides a measure about the average number of yes or no questions that we need to determine the outcome of a random variable. Right, and what does that mean? So for instance, let's consider, say, X is a random variable that takes the following 4 outcomes, A, B, C, D, with the corresponding probability given like that, right? Then you ask, on average, what's the minimum number of questions we need to ask to determine the sample values of X, right? Say I take a sample of the X, right? Then it could be A, B, C, D, any of them, right? So only I know, then I ask you to guess what that X value is. And the one optimal strategy would be like you ask the questions related to the most probable state first, right? In this case, it's A. You ask whether it's A. If the answer is yes, then you nailed the value by 1 question, right? The probability is 1/2 because the probability of A is 1/2. But the answer, if it's no, then you continue, right? Then you will ask the next ask about the next most probable state, which is B. And then you ask, is it B? If it's yes, then you get that, right? So then the probability is 1/4. Otherwise, you continue with the C. Once you the answer for the third question is no, then we must know it will be B. Will be D, right? Then on average, the total number of questions we asked will be, for A, we ask the first question, right? The probability is 1/2. If it's no, right, then we ask our second question, and we get the probability 1/4 to be B. Otherwise, we ask our third question, and we have 1/8 probability to get the state to be the C. If the answer is still no, then the state must be be D, right? And we don't ask additional questions here because it's obvious. So there's no other states available, right? So possible states. So then it's still a third we ask 3 questions, right? So the probability for the D is 1/8. Then on average, 1.75. That's the average number of questions asked, right, in this example. But then how does that relate to the entropy? Now, if you look at that, actually applying the formula of the entropy, right? So we get the following formula compared to what we have up over there. The first question we ask actually corresponds to log 2 of 1/2. 1/2 is the probability for the A, right? Same thing, 2 for the B. Second question corresponds to log 2 of 1/4. The third question, log 2 of 1/8, right? That's actually exactly what we have over here. And we get the answer 1.75. So then make this connection, right? Really, the building block over here, the negative log 2 pxi would correspond to the number of questions we need to ask to specify the outcome, right? And here, instead of the questions, the unit, it's called bit because we use base 2, right? When we use base 2 for the log, then the unit for the entropy is bit. Some other common bases like E, the natural log, right? So then it's net, and there's base 10, right? So, but really, this negative of log times the negative log of the probability mass matrix, probability mass function evaluate the states, right? So it gives the number of bits needed to specify the outcome xi. And of course, the log function, so it's the negative log, right? So it's a decreasing function. The smaller the probability, the bigger, right, the corresponding value. That's why less likely event requires more bits. And of course, then the number of bits will be weighted by the probability that the state occurs. That's why you see this p multiplied with that, right? Then we need to sum up with all the possible states. That's the summation. So then really what's going on is like the entropy provides an average number of bits needed to encode the random variable, right? And so entropy, in other words, it measures the average uncertainty in the random variable, right? So high entropy implies more uncertainty. And in the extreme case, for instance, you can think of, okay, it's not a random variable, right? It's deterministic, right? Then the random variable will take just one value and with probability 1. So this will be 1, log 1 will be 0, right? So then the entropy will be 0. From another extreme, of course, you can ask, well, then what would be the distribution here that can maximize the entropy, right? We know minimizing the entropy would be 0, like deterministic, right? So the x will be deterministic. But in this example, we can think, right, what would be the distribution that will maximize the entropy. It turns out, say, if we put some, of course, we need some constraint on the random variable, right? If the, say, given a random variable, the lower bound is fixed and the upper bound is fixed, but otherwise there's no other constraint on it, right? Then the one to maximize the entropy would be the uniform distribution. Of course, here I'm assuming like it's a continuous random variable, right? And also when, say, I know the variance of random variable, right? So that's another situation. Then the one to maximize the corresponding random variable would be the Gaussian distribution. Among all the continuous random variables with the same variance, the Gaussian distribution would be the one to maximize the entropy. And we can, because we know the analytic expression of the probability density function, right? Then we can calculate the direct analytically the entropy turns out to be given by this formula where that's a variance. And then here there are some just constant values And more generally, if we consider high dimensional, say a d-dimensional Gaussian random variable, and with some variance matrix sigma, then the corresponding entropy would be given like this. So it's log of the determinant of the variance matrix times 1/2, then plus some constant terms depending on the dimension d over there. And we will come back to this formulas in a little bit, of course. So the details about the results can be found in chapter 12 of the book I mentioned before. Extending beyond the entropy array, there are other versions of the entropy. First, here, that's just the multi-dimensional version of the differential entropy, where it's just the x can take values in some higher dimensional Euclidean space, right? Then the formula will be the same as before. Here, I just dropped off the bases because we can convert from different between different bases, right? It's just different bases would need to different unit for the entropy.
Oh, one question, but
yes,
but in general, this would be log 2, right? Like in a
oh
normal definition.
yeah. For actually throughout the remaining of the talk, I assume that it's log 2. But you can use log 10 or log e as well. Right? So
yeah, but then it was how that was, if I remember correctly, that was how it was related to the binary questions, right? Because I think that
yeah,
how
exactly, exactly. The yes/no question, exactly. And that's how information are stored in our usual computer, not quantum computer, right? So the usual computer, the binary digits. Yes. Then there's another concept called joint entropy. Say I have two random variables, right? Then the joint entropy measures the uncertainty of the two random variables together. But then what we plug in over there would be the joint probability density function. That's it. Right? And the conditional entropy, say, what if, say I want to compute the entropy for a random variable, but I already knew some information about another random variable, right? Then there's conditioning on that. So the conditional entropy quantifies the uncertainty of one random variable y, say, giving already we know that we know some information about the x. So then in this case, the only thing changes is within the log where we put the conditional probability density function there. And we have the following chain rule. So the joint entropy is the entropy of the x plus the conditional entropy of y giving x, right? Or the other way, you can write it in this way, right? But the formula really it's just coming from the fact that the joint probability is the product between the conditional probability density with the marginal density itself over there, right? So it's just coming from the basic facts over there. And then there's another concept called mutual information. The mutual information between two random variables, it measures to what extent the two random variables are independent of each other. Right? So and in the log we put the ratio between p as the joint density and the product of the two marginal density. Of course, we know if x and y, if they are independent of each other, then the joint will be the product here. So then the ratio will be exactly 1. So the mutual information will be 0 in that case. So that's an extreme situation. Right? It measures the independency. And we have, of course, it's symmetric in the definition, right? So the mutual information between y and x and y is the same as the mutual information between y and x. And so the mutual information is also linked to the entropy we introduced previously through the formula over here. Of course, it's kind of a if it's the first time for us to see it, right, it's not clear. But if you look at it in the spirit of a Venn diagram, it becomes very clear. For instance, this is my entropy for x, right? My entropy for the y. Then the mutual information is the overlap between these two, and then the conditional entropy is just whatever the entropy for the x except the overlap part, because I already know, because it's conditioning on y, right? Then whatever I know about the y, I already know, right? So then that's why this is the part left. And the joint entropy would be the whole thing here, right? And also from the identity over here, we have a particular case. For instance, the mutual information from between x and x itself. Then it's just the entropy of the x. Right. All right. So these are just a quick overview of some basic concepts from the information theory that we will see in the build up. Then moving on to the actual framework about the causal inference. Right. So I was trying to produce a graphic view of the 3 steps, but I was of the 4 steps. I was running out of time, and so I asked our chatbot, AI chatbot, to give me a fancy graphic rendering. Right, that's what it comes up. But anyway, we can live with it. So the first step, we do data compression. Right, say I have so a PDE solution, right? So I want to compress it and get some time series, to compress out the spatial dependence. Once I have the time series, I can we build up a function library among the variables, and the goal is to trim down the function libraries. So we don't want to use all the function libraries, hopefully, right? So that's where we get the sparsity. And how do we train them? So that's where the causation entropy comes into play. Once we select the terms using the causation entropy, then we can do the parameter estimation to estimate the coefficients for each of the terms. Right? That's the idea. So the main novelty is here, because the other 3 steps are just classical, right? You do, for instance, data-driven modeling, where you do regression, for instance, to determine an inverse model. And the result is in this nonlinear dynamics paper. So the first step is the training data, right? The training data would be some time series, right? So the multiple time series. Say I have n of them, right? And for each variable, I have a n sub t number of data points. So each data point correspond to a time instant, for instance, and say these time series are equally sampled with a fixed times step. Right. So really, what's going on? For instance, just take for instance here, I have a spatial temporal field for a solution. And in this case, it's coming from stochastic Burger's equation. So here is my space, here's my time, right? But to compress the data, I do POD, right? Proper orthogonal decomposition. So that's my POD modes. Then I project the solution onto the learned POD modes. That's my time series, right? So for instance, I plot some A1, A3, A5. Of course, how many time series we need, that will depend on like what is the minimum number of POD bases we need to use in order to get a good representation of the original data point or original solution field. Right? So, but then the training data would be a discretization in time of the time series we get this way. Right? That's how we get the training data. Then once I have the training data, right? So we know which variables we need to model, right? So it's A1, A2, all the way up to a certain point, right? So these are the vector field identified by A there. And I need to construct some candidate functions that I can use on the right-hand side of the equation for the A, right? So which we call feature library. The feature library, for instance, it could be terms like a polynomial. For instance, polynomial functions, say A1 times A1, A1 times A2, etc. Right? So, or there could be sine, cosine functions, but really, what functions we put in there will depend on the problems, the physics problems we have, right? And some of the functions may even not depend on the state over there, right? It could be some time dependent, some known time dependent function that serves as a forcing term in the model, right? If our physical information would indicate that such a function would be needed. Then once you have the feature library, essentially we assume, for instance, the equation for each of the time series, right, or each of the variable AI would be written in the following form, where it's a linear combination of the building block functions in the feature library, right? Then plus some noise, because most likely this linear combination may not match exactly with the time derivative in the data, right? So there's some mismatch, and then you can use some noise terms to model to capture at least the variance in the residual of this process. But if we would take all the coefficients Cij to be non-zero, then we get a full run, right? So every term appears in there, right? It's not sparse at all, right? Instead, we want to enforce some sparsity and to make sure some of theCijs to be actually exactly zero. And how do we do that? The way to do it is to rank these building block function terms, right? I rank the importance of these terms and I only keep the top few percent. So give me a threshold, how many terms I can include in the right hand side, right? So I just keep the first, the top terms, right, up to a certain percentage, and set all the remaining terms to be zero. Yes.
One question, maybe you already mentioned, I'm sorry if you already mentioned, but like, so how did you select this rank? Like, what is the criteria to define what
Yeah,
will be the
that's
rank?
what I'm going to talk about. That's a very
Oh,
good
okay,
question. So yeah, so
okay.
how do we rank them? That's the next question, right? So we need to determine the model structure, right? So the importance, that's where the causation entropy comes into play. So say I want to determine a particular function library, a particular function in the library fj. How important is this function to the dynamics of the AI, the ith variable in the vector, right? I want to model. Then what I do is I look. So this is the causation entropy, how it's constructed. I looked at the information provided to the derivative of the AI by the function fj, conditioned on the fact that I know all the remaining functions in the library, right? And how is this defined? So it's just the difference of two conditional entropy. So when I know every function, because I have the training data, right? So if I know the function library, if I know the training data, then I know the information over here, right? So I compute the conditional entropy of the derivative of AI conditioned on the information provided in the whole library. So there's uncertainty in there, right? Then I also compute the conditional entropy where I just exclude the fj term. And then I take the difference. What does it mean? Then it means, because if I exclude this, I have less information, then the conditional entropy would be higher compared to I use all the information of the library, right? But if then I measure the difference, if the difference is very tiny, then it means the contribution of the fj to the AI equation is small. On the other hand, if the difference is very big, then I know take away the fj contribution would have a big impact, right? So that's how I quantify. So the definition, that's the definition of the causation entropy, right? So it quantifies the additional information fj brings into the dynamics of the AI, conditioned on the fact that if we know the other library function. That's why in this procedure, I need a predefined function library, right? I only consider the building block functions must be selected from the library. And of course, there are some properties, right? So this quantity is always non-negative, right? Because when you remove a conditioning, then the conditional entropy cannot be less than what we know over here. It's always a non-negative. And the larger conditional entropy value would imply bigger effects of the Fj on the dynamics of the AI. And so this concept, it's not proposed by us. It's from Swain and Bolt. There's a paper by them back in 2014 in Physics D. Their initial motivation was in the context of network inference, where they want to detect a direct connection and filter out indirect connection. For instance, here is a network. When you look at the bottom here, this node, there's a direct connection, right? And this node with that node, there is a direct connection. But there's no direct connection from this one to that one, right? So prior to this causation entropy, when they were testing some other candidates, like entropy variant proposed in the literature, when they apply it, they would also pick up a connection here, from here to there, because it's kind of an indirect, right? So there's an indirect connection. So they want to distinguish direct connection with the indirect connection. So that's the idea, and the causation entropy was able to do the job.
It looks somehow similar to what you were showing before about the mutual information, right? Like
Well, that's a very good point. It will come in the next slide. Thank you for pointing out that.
Okay.
It looks like you have so many slides. Just joke. But there's a little caution over here. Causation entropy, it does not detect the true causality. When we say causality, what caused what, right? But here, it does not detect the true causality. Instead, it's just quantify uncertainty reduction. For instance, to what extent this Fj would help improve the modeling of AI, right? And the comment you will see after the next slides, you will see why it does not detect true causality. And back to what Juan said, right? Really, there's a connection to mutual information. Why? So this is my definition of the causation entropy, right? And if I want to generalize it, right, so to make it less busy, say I put the causation entropy from Z to X conditioned on some random variable Y, right? Then that's a formula, just the same as what we defined over there. That's a formula. And remember, I mentioned mutual information before, right? So it's giving like this. That's the common part when you have remember the Venn diagram, right? X, Z, it's the overlap part in the Venn diagram, right? How is this mutual information connected with the causation entropy? Actually, if you take the mutual information and allow for conditioning, see here, I allow for conditioning on the Y, then I put conditioning on the Y everywhere in the equation, right? Now when you do that, and if you look at the middle equation here, right, with the causation entropy, it's exactly the same. It's exactly the same, except here the condition in the order is different, but that does not matter, right? They're the same. So the, in other words, conditional mutual information is actually causation entropy, right? But we know the mutual information, right? It does not matter whether you look at the mutual information between X and Z or the Z and X, right? They are symmetric, even if we put the conditioning on that. That's the reason. So this, because they are the same, right? So there's no causal effect. There's no real causal effects in there, right? Because this causal entropy from Z to X conditioning on Y is the same as the entropy from X to Z conditioning on Y. They are symmetric. Then you cannot really say which one caused another one, right? Because of the symmetry over there. But it's just a measure, as I said over here, right? It's just a measure of uncertainty reduction. Of course, on the Venn diagram, the causation entropy between X and Z, when conditioning on Y, right, it's just the part that I highlighted over there. If you just look at the mutual information between X and Z, then it's an overlap over here. But now we have the conditioning on Y, right? So that's why this part gets excluded. Only this part remains. So it's really the conditional mutual information, the concept we are using over here. Of course, you may ask why then you don't call it conditional mutual information. It's just for historical reasons. Like the work over here, the proposed the name causation entropy, and it was usually in the context of reduced order modeling. But when I was looking in the literature about conditional mutual information, of course, this concept, it was introduced shortly after Shannon's initial work. And there's a reference. This is not the earliest one, but I find it's a nice reference over there. But only recently, the concept of a conditional mutual information has been used in the context of model identification. So here are two papers I put, and these papers are also cited in my paper with Nanchen. I think that sort of answered the question why the concept instead of using conditional mutual information.
Yeah.
Yeah. What?
No, I was saying, yeah, thank you for answering.
Okay, yes. That's the reason. But when you look at it, so usually say the reduced order models, right, depending on the applications, the dimension could be high, right? The dimension could be high. Then the random variables over here, for instance, the function library there could be many terms in there. Then we really remember the entropy that involves the probability density function, right? We need, in order to compute these terms, we need to estimate the probability density. It's high dimensional probability density functions. Then we need to do high dimensional numerical integrations because there's integrations involved in the entropy definition, right? So all these are computationally challenging. So what we do here is instead of actually computing them, we do Gaussian approximations. If you remember, I recall there was a situation where when you only know the variance, right, then the random variable that maximizes the entropy is actually the Gaussian distribution. And in the formula, we can derive the analytic formulas for the conditional, for the entropy over there. And it involves the log of the determinant of the covariance matrix of the random variables involved, right? So we just need to, because once we have the time series, estimating the covariance matrix, it's easy, right? Of course, if we want to estimate it robustly, then we need a sufficient amount of data, right? Then we need to calculate the log determinant. So we avoid the whole complexity of estimating the PDFs and the numerical integrations this way. So that's the key here to get access to some to be able to apply the method to some high dimensional problems. We only need to calculate the log determinant. Okay, and the value over here, another thing to point out is that when you scale the random variable, the causation entropy number will not change. It's just because of this nice property, right? So it does not scaling of the random variables by a constant does not change the causation entropy value. It has an effect. It has an important implication because on the right-hand side, right, we haven't done any parameter estimation yet, so we don't know the coefficients in front of each of the library function. Right, we only know the library function because we constructed them, for instance, polynomials, but we don't know the coefficients in front of it. But the property over here says that it does not matter, right? We don't need to know the coefficient. So that's the key to separate the causal inference part with the actual parameter estimation part, right? Then, but once we have this, say we perform the estimation of this causation entropy for each of the Fj and each of the Ai, right? Then we can rank the importance of each of the Fj's in for instance, in the equation of the AI, right? Then we can do cutoff strategy. Say I only want to keep the top 20%, right, or top 30%. Then we just need to move the cutoff line to get the sparsity we want, right? Then after doing this, we get the desired terms that we want to include in the parameter estimation, right? So then we can rewrite the equation in this way, where the matrix involves the building block terms we want to identify, we already identified, and the theta would be the parameter, the model parameter, right? Then we do, for instance, we can apply our maximum likelihood estimation to determine the theta and also the variance in the noise term over there. So that's the procedure, right? So the key is just the causation entropy part and the approximation formula, the Gaussian approximation formula. The rest is standard in the reduced order modeling techniques. Okay. Then with that, I can move on with to an application to the Krull-Modius-Sieraszynski equation. So the Krull-Modius-Sieraszynski equation, it's a one-dimensional PDE that can support chaotic dynamics, right? And a nice thing about the equation is like there are parameters. That's the equation. It's a fourth order scalar DD where the biharmonic terms is stabilizing. And here, this is a Laplace, but with the wrong sign. The D is positive, so negative D, so it creates instability. And of course, then there's a nonlinear interactions. And we're seeing periodic boundary conditions and some mean zero condition. Here, it's just in order to move the zeroth modes from there, right? So we have sine, cosine modes essentially because of the periodic boundary condition. When we change the parameters over here, the Krull-Modius-Sieraszynski can have a different types of chaotic dynamics. Some like for instance, when we use increase the D or reduce the mu over here, so we will have increasingly many unstable modes in the dynamics to make the dynamics more chaotic, and then the corresponding reduced order modeling and part will become more difficult because you have more and more unstable modes in the system, right? So then arguably one may need to include all the unstable modes in the reduced order models. So that will push high the dimension. So we have a parameter to control, right? So like how high the reduced order models need to be. So then it creates different levels of difficulty to test the method. And here we set in a parameter regime where D is 1L, the length of the spatial domain is 20 pi, and nu is the parameter where, for instance, here I presented a bifurcation diagram. When nu is large, then when nu is large, there are less unstable modes, right? So for instance, here is just a steady state. Then there's a bifurcation coming out with periodic oscillations. So here I just plotted the local extrema of the energy, the kinetic energy of the U, right? So that's why when the local extreme is a constant, then it says that the solution U is not fluctuating, right? It's a constant. Then it becomes oscillating between two, like the global minimum and global maximum, right? Then it's really a periodic orbit. Then it moves into chaotic dynamics. Still chaotic. Now in this region, you see it's oscillating sort of between a minimum and maximum, right? But there's a fluctuation around. So it's kind of a quasi-periodic dynamics. Then it goes back to chaotic, and then it goes back to simple dynamics, right? So there's really, when we move the mu, all sorts of dynamics can happen. And for the results presented below, it's going to be for the nu equals 8. It's really close to the transition here, transition from chaos back to simple dynamics. So we intentionally picked up the value 8 over here, just sit on the boundary of the transition. and we'll see how it performs. So there are two experiments. Two experiments. So first, there's a simple proof of concept test to do. It's like I use the Fourier basis to decompose my solution. Right? So I project the spatial temporal field onto the Fourier basis, where we have cosine and sine modes. We don't have the zeroth mode because of the mean zero condition I mentioned. Then, of course, we can project the PDE onto this mode to get the Fourier Galerkin system. Right? Looking like that. A key point here is that here is the linear term and nonlinearity, right? The nonlinearity, the coefficient of the nonlinearity, most of them are zero, identically zero in this example. So it's like naturally we have a sparse system. The KSE, the Kuramoto-Sierczynski itself, under the Fourier basis, it has a sparse structure. Then the idea is like, can the causation method be able to identify this sparse structure, right? And what we do is we pick up the round dimension 20, right? Then the feature library, it includes linear terms, A1 through A20, right? A20, so it's 20 dimensional. Then the quadratic term, because the Kuramoto-Sierczynski itself is a quadratic model. So that's why we only keep up to quadratic nonlinearity. Then because it's 20, right? Then the total number of functions in the feature library is 230. Right? Now imagine if you want to compute the causation entropy to compute the probability density function for a random variable with 230 dimension, right? It's impossible. But the Gaussian approximation helped here. Right, so if we don't drop any terms, of course, in the full ROM, right, there will be 4,600 terms. And then we estimate each of the causation entropy, right? Then in total, there will be 4,600 total causation entropy values we need to compute. And here I organized it in this way. The equation for the A1, so we have 230 coefficients, right? Equation 1, equation 2, equation 3, etc. It's organized in this way. So the equation 1, the causation entropy coefficients are displayed here in the first vertical column, then second, third, etc. Now, what we see here is a very interesting phenomena. It's like causation entropy values. There's a gap separating the important ones with like the rest, the cloud down there. Right, that actually suggests a very nice place to cut, right? So where to cut off, for instance, I put two cutoff choices over here and over here. So there's within this band, there are a few terms for within there, right? And in the next page, I'm going to show you the results where I cut. It's more severe here, right? So I cut off along the red. And the panel here shows the structure, sparsity structure of the true Fourier Galerkin model. So each row here indicates one equation. So we have 20 equations, so 20 rows. And the column corresponds to the 230 library function, right? For instance, if you see a black dot over here, meaning that the first function will appear in the first equation. Here, the second function will appear in the second equation, etc. Remember, this is the linear part because I have A1 through A20, right? It's just the linear part on the diagonal. Then there are nonlinear interactions. We see this sparse structure. And the second row shows what we get from the causation entropy when we put the cutoff to the red one. Yeah, right. So that's the structure we identified. And when we look at the difference, there are a couple of terms missing from the causation entropy. In total, for the Galerkin system, we have 295 terms. And for the causation entropy, there are 283 non-zero terms. And there are 12 terms missing in the causation based ROMs. And these terms fall within this band, the terms that we missed fall within there. So it's pretty good, right? We missed a few terms. Of course, the question is to what extent these terms would participate in the dynamics. Then there's the modeling, learning the parameters, right? So here I show the true coefficients for the linear part of the true Galerkin system compared to the learned dynamics. The difference, it's on the order of 10 to the -3. Right? So it's negligible. And the nonlinearity, truth compared to the learned. And the difference, we see more pronounced differences because we missed the terms. The most difference appears, we checked, the most differences appeared in the places where we missed the terms. And it turns out when we look at the results, this is a solution field from the true dynamics, and this is from the reconstruction. It's chaotic, right? So we should not expect the solution field to match. And actually here I showed you on a very long time simulation. So the T, the time window here, it's well beyond the training window where the training data I just pick up from this tiny window. And here the it's 10 to the power 5. So we get good visual reproduction of the different features appearing in the solution field, right? And on the statistical level, we compare the energy spectrum for the cosine mode, sine mode, they match almost perfectly. And the probability density of the kinetic energy over here, so they also match an autocorrelation function. And we use different statistics metrics, right? They all match well. And another thing to notice is like you see how non-Gaussian the probability density function is. Remember, I used the Gaussian approximation to compute the causation entropy, right? But the model we have over here, really, it has highly non-Gaussian dynamics. And the method still worked. So it's kind of, there's a robustness in the approximation, right? So it worked way beyond this Gaussian assumption where we used it to get the approximation formula for the causation entropy.
Do you have any guesses why making this assumption that apparently it should be counterintuitive works? Like
Actually, yeah, that's a very good question. So remember, the Gaussian actually gives the maximum among all the, because once we have data, right, so then we can get the variance, meaning that we don't, even though we don't know what distribution the random variable would follow, but the variance would be the same. So they share the same variance. And remember, previously I mentioned, if we only know the variance, then the Gaussian is the one that maximizes the entropy. I think this is something connected with that, but of course it's just a guess, right? We need to test more. For the moment, there's no theoretical proof to show that it will always work, right? So then we need to find where it breaks. It's still in the process, but that's a very good question. Thank you. Okay, let me move on now. We had our first proof of concept experiment, right? Then I want to move on, see what if we use a data-driven basis, say, for instance, a proper orthogonal decomposition, right? But what do we realize it? Once you use a data-driven basis, for instance, the POD here, the POD Galerkin system itself is no longer sparse. It's not like the sparse structure we had before for the Fourier case. For instance, here I showed you, again, it's a 20-dimensional POD Galerkin, right? So we have in total 4,600 terms in this 20-dimensional POD Galerkin. And I look at just the absolute value of the model coefficients because it's a POD Galerkin. It's by directly projecting the PDE. So I know I can compute exactly, right? So I mean, up to numerical error, right? So the coefficient. You see, most of the coefficients are fall within this range, like 10 to the -4, 10 to the -3. Only very few terms are zero, and extremely small, right? When you add these terms together, it's less than 1%. So it's not sparse at all. the POD Galerkin system itself. Then there's no hope, right? It says over here, when we calculate the using causation entropy, it shows that there's no gap, right? So then we need to really pick up, for instance, you just specify sparsity level. Say I only keep the first 10% or 20%, then you cut, right? So that's how it will work. But how does that perform? For instance, here, this is like we assume 20% sparsity, and we look at the performance long-term dynamics, right? Again, spatial temporal field comparison and some statistics like what we saw before. They match well, right? For 20% sparsity. Of course, you may ask, okay, what if you further reduce, right? Then that really depends on like what is the purpose. We know for sure at a certain point it will break if our purpose is to capture the long-term dynamics, right? Actually, if we go down like a cut to 30% sparsity, when we do really long simulation, we can already see problems. Over a shorter time window, that's okay, but when we do long simulation, things will break. For instance, the solution will settle down to some periodic dynamics or traveling waves kind of dynamics, for instance, right? But then it's depending on the purpose. So that brings me to the last experiment about the data simulation with partial observation. So what we do is like we try to recover some unobserved dynamics and we will use some severely truncated ROM model. The setup is the following. So first, within the parameter region, we saw, right, the POD mode, the first three mode, it captures 63% of the kinetic energy. Then the next 7 modes capture about 35%, and the remaining capture maybe 1% of the kinetic energy. So what do? We observe only the first 3 modes, and we want to reconstruct the remaining mode, remaining energetic mode, right? And we use only 10% of the terms, meaning that the sparsity will be 90%. There are, because in total there are 230 terms in the library, right? Then we only keep 23 terms, so very few terms. And as a benchmark, what we do is we take the POD Galerkin because we know the coefficients, right? Then we do a hard thresholding truncation to keep only the first the 23 terms, each equation, right? We keep only 23 terms with the biggest coefficient in absolute value, right? And once we identify those terms, then we relearn the coefficient, because when we cut off terms, then the coefficient is expected to change, right? So we relearn the identified model through parameter estimation, which we call a thresholded Galerkin system. And then we compare the performance using the ensemble common filter, right? We pick up the simplest data simulation procedure just to keep it simple. Right? And that's what we get. So these are the observed dynamics, Y1 through Y3, and Y4 through Y15 I show over here, the one from, they are unobserved, right? They are recovered through the data simulation procedure using the causation-based ROM, where we use the 90% sparsity. You see, there's a very good recovery of the unobserved dynamics, even though when you look at the dynamics over here, actually it's similar level. The energy contained in these unobserved modes are similar compared to the observed one. Right? It's very energetic modes there. Then compared to the benchmark, the threshold POD, you see less good performance over there across the board. And something interesting we observed is like, especially when, for instance, this is a true unobserved dynamics, when there are some transition happening in the short time window, right? The x-axis, the horizontal axis is the time, right? So some transition happening. And the causation entropy was able to capture almost perfectly this transition, but when you look at the threshold POD, it missed completely. Right. Of course, then what's really going on? Why the threshold POD failed? Here, I guess that shows another importance, right? So about the causation entropy, it was able to rank the terms, right? So here we rank the terms using the coefficients in the POD, which seems to be not sufficient. It's not the magnitude of the coefficient that plays the role. It's really something behind it. It's a dynamic feature, right? And we think the causation entropy was able to capture some of the dynamic information in there. And that's all I want to share today. So we introduced a method called causation entropy from the information theory, right? That allows us to rank the importance of the functions in a predefined feature library. This way we can get a hierarchy of reduced order models with different spacities while still maintaining good performance depending on their applications. I mean, the sparsity level we can get would depend on the particular applications we have, right? And then there's the Gaussian approximation behind that help us to get access to this causation entropy values for even relatively high dimensional problems. So of course, if we further push the dimension of the ROMs at a certain point, the log determinants will become even the log determinant will become an issue, right? So, but there are efficient strategies existing method there to compute log determinant, right? Then there are other methods, for instance, using greedy algorithms to trim the number of library functions over there. And I showed you the results for deterministic model, right? So then what happens when we have noise or like stochastic systems, right? So that is still up for exploration. And with that, I thank you for your attention.
Thank you so much, Honghu. Do we have any questions from the audience? Maybe looks like we don't. Maybe I can have another question. I asked too many things today, but
No.
did you you had like these two ways, like for example in the previous images that you show, like you can do like this POD lurking, and you can also do the like in no the one up next one, yeah where you had like the where you had like the one using the POD lurking and the also causation based, and then you show that it actually it works a bit better. But maybe did you also compare like with respect to time, like is like
With
or
respect
that
to time.
no, but like the computation time, like
The computation time for no. So the once you have the model identified, they will perform because the model is the structure. It's just a stochastic SDE, right? The number of terms will be the same.
oh
It's
okay,
just the num. It's just the constitutive terms, like which monomials you had in there is different, but the number of
oh okay.
monomials is the same. So the
So since the
computation
number
time
of
is the
terms is
same.
the same, it will be the same computational time.
Yes,
Okay.
yes. But
And
there's a catch, right? See, the identification, it's the computation of the causation entropy. That's where it takes time, right? Because you need to here we get away with the the Gaussian approximation, right? But when you go further, increase the dimension, then the computation. That's what I mentioned. If you want to compute the log determinant, there, because we have many terms, right? So you need to compute log determinant of high dimensional matrices for many times.
yeah.
Then that's where the computation is. So it's mainly the offline computation.
Oh okay.
Yeah.
Yeah, I see. Okay. Thank you, Honghu. Do we have any other questions from the audience? Uh, Maybe it looks like we do not. So Yeah, thank you so much, Honghu. I will convey your regards to Jerome. Actually, I heard him that he just came
Thank you.
a few minutes ago, so I want to tell him that you say hi. And also
Great.
thank you so much for your time today, and also thank you everyone for attending this week's seminar.
Sure, my pleasure. Thank you so much, everyone. Thank you, Juan.
Okay, bye. Have a
Bye.
good week, everyone.